bit. So last week we talked about how everything is made up of atoms, right? But these individual particles that are called atoms can actually be arranged in like a number of different ways. So last week we already touched on ions. So, but this week we'll also bring in molecules. So as you can see on the slide here, an atom is just your singular particle and it's neutral, so it has no charge, versus an ion, which is an atom but with a charge. The molecule, again, is something different, and then it's just atoms that are combined, two or more atoms that are bonded together, so they are chemically combined together. Is that?
Yeah, cool. And we'll explain more about molecules later on when we get through these slides. Yeah, so here are just some examples of atoms, ions, and molecules. With an atom, it's basically just an element from the periodic table, like magnesium or calcium, but only the atoms themselves. And they don't have any charge, and they're just like metal, magnesium metal. If it's pure, then it'll be only consisting of atoms. Whereas for ions, as we have explained earlier, the magnesium or calcium or just any other type of ion will have a certain charge on them. And that's because they've either lost or gained electrons, so there's an imbalance of charge causing it to be positively or negatively charged. And an example of molecules is water. Now, water is made of oxygen and hydrogen, but they're joined together with their like special bonds that we're going to touch on soon. And basically, you just see lots of tiny little oxygen and hydrogen like atoms, and they're joined together, but there's multiple. Like water is H2O. So for every molecule, you're going to have 2 hydrogens and 1 oxygen. And here's just a simple diagram. As you can see, the whitish atoms will be the hydrogen because there's 2 of them, and the red one will be oxygen. So a single water molecule looks like that on the left, and then water molecules, all put together, are seen on the right, but you see that between them, they're not joined together. They're just independent molecules, but just bunched up all into one.
Cool. Let's have a look at the 3 states. So I'm sure most of you would be familiar with this because, like, we all know there's solids, liquids, and gases, right? So a solid, I'll just give you a quick particle level kind of description. So a solid is where attractive forces actually keep the individual particles very tightly together. So that's why your solid is solid. Like, you can't squish it down or compact it because the particles are already too close together. And then the liquid, the particles are still pretty close together, but then the particles can actually like move past each other. So it's a bit like if you imagine maybe marbles rolling around in the bucket. So they are able to flow past each other, and that's why liquids fill up the space, and we can pour liquids around and stuff. And then gas, the particles are really, really far apart compared to solids and liquids, and there's basically no attraction between the individual particles of gas. So because there's so much space, we can easily compress them and stuff like that. So yeah, the particles, the individual particles are always moving, but the gas particles move the most.
Yeah, and that is something we'll delve into later, like a concept called kinetic energy in relation to particles. And yeah, so that's when we'll explain why these particles are all moving and how the movement or the speed of the particles affects their state. And yeah, do take note of this little fun fact down here. We will explain why that is very shortly.
So, as in right now. Physical processes. Emily, do you want to do this slide?
Yeah. So there are basically 4 fundamental states of matter. We've got solid, liquid, and gas, as we just touched on. However, there's also one called plasma, but we're not really going to worry about that because it's not very common. We don't really see it in our day-to-day lives. But within these sort of states, they undergo a physical process. And these are physical changes because they're reversible, given that we have adequate conditions and the capacities. For example, if we just take water or boiling water, we can condense it by cooling it down to form a liquid, which is just liquid water that we drink. And furthermore, we can also freeze it by applying more, coolness to reduce the temperature, and it will become a solid, which is ice. And yeah, but in this orange word, sublimation is maybe something that you guys have not heard of, and it's when a solid goes straight to a gas. It basically skips the process of becoming a liquid. And also the reverse process is known as desublimation, but we don't really see that too often. But yeah, an example of sublimation is just dry ice. Some of you may have heard of that before. It's basically carbon dioxide that is in a solid form, but it quickly transforms into a gas because of the vast temperature changes and the fact that carbon dioxide is just normally a gas. You know, it's all around us in the air. And when we see it in a solid state, it has to be so cold in order for it to become a gas. And
so it's probably worth noting that like these, because they're physical processes, they don't actually change the particles themselves. So the particles themselves stay the same, but say if it's a solid, your particles are really close together and you melt it, so then the particles become a little further away and they can slide around over each other like a liquid. And then when it's evaporated, the particles are really far apart. So it's only changing like the amount of energy they have or the distance between the particles. It's not actually changing the particles themselves.
Yeah.
Cool. Okay. Why does water expand when it freezes?
Yeah.
Okay, that's a good question. So that's like probably the reason why you're not going to put some water in a glass and then freeze it, because then your glass will shatter. Or maybe that's even happened with like plastic bottles. If you've tried to like freeze a bottle of water and it expands and your plastic bottle breaks, yeah, that might be why. So we can have a look at what is kind of like an interesting compound. I guess it's a bit different from a lot of other compounds. So if you can tell from the diagram, in liquid water, so it's on the right, the molecules are really close together, so it's quite compacted and it takes up less space. But then when it becomes a solid, the molecules actually join together in a very regular way. So they click together to make like a really large crystal lattice structure. And because the molecules are so orderly, arranged in an orderly way, it actually takes up more space when it's in solid form. So that's why ice, it's less dense than water because it takes up more space, and that's why ice floats on water.
Yeah. So yeah, that's it. So now we're gonna be investigating how we basically determine whether a change is chemical or physical, and we ask ourselves these 3 questions, pretty straightforward, and we're going to apply this to a set of different types of changes for you guys to hopefully identify and use these concepts.
Before we jump into that, the physical changes are what we talked about before, right? So the physical changes, they don't actually change the particles, but then chemical changes are a bit different. So chemical changes, you're actually changing the bonds between the particles, or so within the particle itself. So it'll involve like bond breaking and bond making between atoms. So that's a chemical change.
Yeah. So yeah, physical chemical changes, we ask ourselves, is the substance the same thing now as it was before? And if it is the same, for example, if we just take boiling water, water's not going to change its properties all of a sudden if it becomes a solid form like ice, or if it's a gas. It's still water. We're still dealing with the same molecules, and the molecules haven't undergone any change. They haven't broken any bonds within the hydrogen and the oxygen atoms. They're all still the same molecules. Whereas if we see a change in color or change in smell, often this will indicate that it was a chemical change, one that cannot be reversed.
Or reversed easily, yeah.
Yeah.
The change can be reversed easily, like take water again. Say if you want to turn water into a solid, you just chuck in the freezer, and if you want ice to, turn back to water, you just take it back out. So it's very easily reversed, and that makes it a physical change.
Yeah. And these very simple examples can be applied to a lot of different things. We're just using water as a very basic one, just for you guys to get an idea of the differences between chemical and physical changes.
All right. Should we put them in the deep end? So we have some food processes here on the screen, and I guess we'll just, should we do it like let anyone ask, or should we just choose people to answer?
Well, for the first one, if anyone wants to, point out the obvious, boiling water, someone just want to just call out whether it's a physical or a chemical process. Anybody?
It's a physical process.
Awesome.
Very nice.
Yes.
Right. And if we didn't get that one right, then that's a okay.
Yeah.
Second one, making toast. So when we talk about making toast, we're specifically talking about putting the toast in the toaster and cooking the toast. So do we think it's chemical or a physical change?
I think it's a chemical change because there's a difference in the color, and also because the toast can turn like a bit more brown.
That's
and it also releases like a warm smell.
Nice. Yep. Making toast is indeed a chemical change. Good job. Should we have, okay. What about melting ice cream? Anyone else? Physical.
Yeah, good job.
Very easy.
That's right.
Although I would say that melted ice cream refrozen doesn't taste as nice, but and what about baking a cake, as in physically putting it in the oven?
That's a chemical change because you can't unbake a cake and make it a batter again.
Exactly.
Yes, chemical.
All right. What about defrosting frozen chicken?
That's physical because you can freeze it again.
Good job, people. Okay, do we want other people to answer as well? Although the last two get a little bit more tricky, but it's okay. What about a banana? You know how bananas go brown, they get their brown spots. What sort of change would that be? Yeah, thank you, Sophie. You've been answering. Oh, good job, people. Yeah, it would be a chemical change. You can't unbrown a banana. What about dissolving jelly crystals? So what do we think? What sort of change do we think this is? Should we get people to vote on it?
This is quite a tough one.
All right, if you think it's chemical, put your hand, I don't know, if you have your camera on, put your hand up, or like, I don't know.
I think there's like a little tool where you can just raise your hand, but not sure.
Oh, we're getting some mixed answers. Chemical. Okay. Any other answers? Any other people
want to justify why they think it's either a chemical or a physical change?
Bella, do you want to tell us about why you think it's physical?
I think you could like turn the jelly crystals back into solids, like there is some sort of way. But like it's just me thinking really.
Oh, yeah. That's a good thinking. I like it. Anyone else? All right, should we explain it? Okay, so dissolving jelly crystals would in fact be a physical change. And if we have a think about it, it's, so good job to people who see physical. So if we think about it, the crystals are, it's like an ionic solid or some sort of, it has a lot of, like particles that are together, and when you put them in water, particles kind of spread out because they're in the water, and then if we want to reverse it, we can actually, if we want to reverse it, we can actually boil off the water. So when you boil off the water, the particles all come together again. So yes, like Vala said, you can actually get crystals back if you, if you want to, for some reason, unmake your jelly. But yeah, so jelly crystals literally, so any dissolving reaction, if you're putting sort of ionic solids in water, all of that will be a physical change because the actual particles themselves. Cool. And the next one, what do we think popping popcorn in the microwave is? That one is a really interesting one. Emily and I actually, yeah.
We were a bit like confused at first, but yeah.
Chemical?
All right, so some people think physical, some people think chemical. Again, it's one of those toss-up ones.
Yeah, it's quite an interesting one. Gotta say, I wasn't actually sure on the answer before I did this. That's a good question, Bella, worth considering. That's what I was thinking as well. Okay, Is it cardia?
Oh no, it's pronounced Khadija.
Khadija. Oh, okay. So Khadija, do you want to? Okay, you go with chemical. You reckon?
I mean, I guess I'll just say my reasoning why I thought it was physical at first. I guess I was just thinking if you have a popcorn kernel, I just thought that it gets popcorn around that one kernel. So, and I don't know why I was thinking I didn't know how to eat popcorn. So if you eat the white bit of the popcorn, then you'll still have the kernel, but you don't. So that's why I think it's chemical.
Ah, interesting.
Good thinking. Anyone else want to have a explain why they're thinking? Sophie, do you want to explain why you think it's chemical, maybe?
I think like it's chemicals is like first of all, I don't think you can like unpop the popcorn and then also like I don't know.
Yeah, no, that's a totally valid point. And you know what? When I heard this question, I was like, you can't unpop popcorn. That is obviously a chemical change. And Emily was like, wait a minute. And I was like, wait a minute. So yeah, no, actually, popping popcorn is a physical change. And I was fully convinced it was a chemical change. So we will quickly explain that actually. So maybe we're like when you see popcorn, you're like, okay, there's like a kernel and then it completely changes to something else, right? It's like a little white puffy thing. Well, actually, apparently, it's only like the kernel, when you put it in the microwave, there's a bit of water in the kernel, and the kernel heats up, and the water heats up, and then it turns to steam, and then just explodes, basically. So the only difference is that it was once inside and now it's outside. So the starchy stuff inside of the kernel, it's actually the same stuff. So it's only a physical change, surprisingly. So you can unpop popcorn. I don't know. Maybe you can try. Okay, cool.
Yeah.
All right, good job. I know that one. All right, matter. Let's go into matter. Is that my one?
So, as we looked at the different types of particles earlier, atoms, ions, and molecules, these particles can also be arranged in different ways, known as elements, compounds, and mixtures. Of course, last week when we saw the elements, we saw them in the periodic table, and they're almost similar to atoms because a single part of an element is just a single atom. So yeah, elements just have many atoms involved. They could either be diatomic or a lattice form, or just one, like a noble gas. So just breaking this down, a diatomic type of element is one that is often found in the halogen gases, halogen gases on the right-hand side of the periodic table. Now, this is in group 17, and it consists of gases like fluorine, chlorine, and iodine. Now, these will always come in the form of a diatomic type of element. So I think actually that might relate more to in the molecule form, which is basically when you have fluorine, but or chlorine, but it joins up as two, it would always come in a set of pairs, which is why it's diatomic. Di meaning two, and atomic just meaning the atom. So whenever we draw something like fluorine, we're going to write it as F2 or Cl2 for chlorine. And but they're still the same element, but they're also known as diatomic because there's two of them. Or they can come in a lattice form, which is basically like the metal elements, as we talked about before, or just one like noble gases, which is in group 18 of the periodic table. And and then
so so elements basically can be atoms, ions, or molecules, but all of the particles inside elements have the same number of protons, so the same atomic number, which makes them the same element as in on the periodic table. Cool. Compounds, moving on.
Yeah. Again, so now moving on to compounds, they're basically just chemical substances made up of two or more different elements in a fixed ratio. So this ratio is very important because if you have a sudden change in ratio, like if we have magnesium chloride, which is an ionic compound. Now magnesium has a charge, the magnesium ion has a charge of 2+. That's just what it does when it becomes an ion. And then chloride ions have a charge of 1-, which means that we need to have two chloride ions in order to balance out with one magnesium ion. So this is what you can call a 1-to-2 ratio, needing one magnesium per two chloride ions. And now this ratio is what determines this compound to be called magnesium chloride. We can't just have a single chloride ion because that would just muck up the ratio, wouldn't be the compound that we want. And this can also be seen in other different examples, mainly in what we like to call ionic compounds, where we have ions of the opposite charges, like a positively charged ion or a negatively charged ions.
So compounds can be ions or molecules because they have to be more than two, so it can't just be like. Okay, and mixtures, last one.
Yeah, so mixtures, this is when they're just like, if you like to use your analogies, like two people holding hands. They're connected, but they're not actually merged in with one another. They don't have bonds that are joined in with one another. And one really good example is if you just think about a smoothie. So in a smoothie, you blend up all your different types of fruits together, but they're all just blended into a mixture. They're not joined. You don't just join like a banana with a blueberry. It's still their own like tiny molecules and compounds, but they don't fully chemically mix. You can think of it as that they physically mix, that if you could somehow separate every like particle of banana and blueberry, you could find them separate because they don't chemically join together.
Yeah, cool. All right, so we can on to the next slide. We'll just separate the pure and the mixtures. So pure substances only contain either one element or one compound. So it's like basically one type of particle. For example, you could have water. So water is made up of like two different elements, right? But it's one molecule, and pure water only has H2O molecules present, making it a pure substance. So if there's only one type of particle present, that makes it pure, as you can see on the diagrams. And then mixture, it's as we've explained, we can have like different types of different types of like elements, ions, compounds, molecules, as long as they're like different types of particles that are put together, basically they're a mixture. So they don't have any different bonds. They're not bonded to the same thing, so they're not identical. Yeah, if it makes sense intuitively if you think about your life.
Yeah. And we'll touch on the bonding part probably next, I think.
Okay, and the next slide has, just a quick graph for you guys to just categorize your knowledge a little bit, because I know we've talked about a whole lot of stuff. Can everyone indicate if they're following along? Is it all good? Yeah, so as you can tell, all matter, you can classify it as pure or mixtures. Within your pure, you can get individual elements or individual compounds, and in mixtures, you can get two different types of mixtures that we'll talk about later. Cool, everyone good?
Yeah, I've just got a question from Shimbavi. Is a smoothie a physical change? So I don't, with physical changes, it often comes with a change of state. Like if you're melting some frozen berries into softer ones, that would be a physical change involving ice. But a smoothie is just like a blend. We're just forcibly putting together all these different particles of like fruit together into a mixture. So I don't.
So yeah, I guess it's where, like, I get what you're saying, like physical changes, and you're just chopping up like the piece of fruit into really, really, really tiny pieces and chucking with something else. So you're not actually changing what the fruit itself actually is, right? So yeah, technically, yeah, but there's no change of state involved.
Yeah.
Cool. Next slide, we'll jump into bonding. So last week we talked a bit about ionic bonding. This week we'll talk a bit more about covalent bonding and intermolecular forces. So that's more about our molecular substances. If we have a look at this diagram here, there are two main types of like forces or attractions that are keeping things together. So the first arrow says intermolecular forces. So inter means between. So the forces are between individual molecules. So you have one molecule here, another molecule here. The intermolecular attraction is between those two. And now there's another type. It's called intramolecular attraction. Small difference. So intra means within the molecule. So if you can tell here, it says hydrogen and chlorine. The full molecule is HCl. It's called hydrogen chloride. And an intramolecular attraction attracts the hydrogen atom and the chlorine atom together. So it's intra, so it's within the atom. So the intramolecular attraction, in this case for hydrogen chloride, is called a covalent bond. So you can see that the H and the C are really, really close together. That's because the covalent bond is really, really strong. So it keeps the two close together, making them one molecule. Versus the intermolecular attraction, represented by the dotted line, it's weaker, so the molecules are kind of further apart, and yeah, that makes them separated. So yeah, when physical changes are made to your substance, it only impacts the intermolecular attractions. So it will only, so if you're like freezing, it becomes close together. If you're boiling, the intermolecular attractions become weaker and they go further apart, basically. Cool.
And to just help you remember which one is which, you can think of inter as like inter-house competitions between different houses. So inter just means between different types of molecules. Not really different types of molecules, but like the same molecule, but just different ones. And yeah, intra, just if you look at prefixes a lot, intra just means within. That's why we see the intramolecular attraction within the hydrogen chloride molecule.
Cool. Should I do this one as well? I will jump a little bit more into covalent bonding. So this is your intramolecular forces. So what exactly is covalent bonding? What's holding these two atoms together? So actually it's about sharing electrons. So last time with ionic bonding, if you remember that far back to last week, it was like a transfer of electrons. So one molecule would have less electron, and they'd come together because it's like negative attracts positive, so opposites attract. In this case, it's a bit different. So covalent bonding is where they actually share the electrons. So if we have a look at the diagram here, the dots are represented on the oxygen, so they're on the big ring around the O, and it has 1, 2, 3, 4, 5, 6 dots. And if you have a look on the periodic table, oxygen is in group 16, meaning it has 6 valence electrons. So if we think back to last week, to make atoms stable, they really like to have a full shell of electrons. So in a full shell would go 2 for the innermost, then 8, and then 8 again. So in this case, O is in your second shell, so it wants 8 electrons. So that's why it's sharing two electrons, one from each of the hydrogen atoms, represented by the crosses. So the crosses are the electrons that technically belong to the hydrogen atom, but they're sharing it with the oxygen. So in that case, the oxygen now has 8 electrons in its outer shell, and the 2 hydrogen atoms also have 2 electrons in the outer shell. So all of them have full outer shells, which they make these compounds very stable and also makes the covalent bond very, very strong.
Cool, and now let's take an even bigger example. Rather than just dealing with water, we can deal with more complex molecules like proteins. Now looking here, proteins look quite big and scary because they have lots of different atoms there. But not to worry, because all the bonds are still very similar. We're seeing still the same type of covalent bonding between each different atom. So for example, here between our carbon and our oxygen, we see a single bond, and it's an intramolecular bond because it is within the molecule. We're not talking about ones that are like connecting entire proteins together. We're just talking about what's happening on the inside. However, we're also going to see double bonds quite often, and that's because double bonds and like triple bonds occur when the number of shared electrons vary. So in this previous example, we saw that water was just sharing their electrons like a pair. So like, like 1 electron pair, meaning that it's like a single bond. Whereas here, when we have a double bond, it'll be sharing 4 electrons or just 2 electron pairs, which is why we see 2 bonds right here. And that can be drawn on a diagram similar to before, using just more circles, more crosses to indicate the electron numbers.
Pretty good. Okay. Oh, I think
Should I reload the slide?
Cool. So if we think back to our flowchart from before, when we categorize mixtures, there are 2 types of mixtures, right? So there's something called homogeneous mixtures and another one called heterogeneous mixtures. So the prefix homo means the same and the prefix hetero means different. If we have a look at these little images right here, homogeneous, based on the green and purple types, is basically a mixture where you have different particles or different substances. It's all very evenly mixed together. So if you have a look, image on the right, the coffee, if everything is very smooth and it's all like one coherent color and there aren't like bits floating around in it, that's basically homogeneous. Homo meaning same, so it's the same throughout the liquid. Heterogeneous, as seen in the little circle, has like clumps of one type of particle and clumps of another type of particle. So it's not fully mixed together, essentially. Like the heterogeneous mixture of coffee, if there are lumps floating around, then you can tell that's not one, it's not exactly the same throughout, which makes it heterogeneous. Just for extension, if you guys are interested, some things like if you're thinking oil and water, why do they not mix? If you made a salad with a vinaigrette, maybe, why do they not mix? It's because of their different polarities. So polarities actually comes back again to bonding, and we can explain it more if you guys are interested. Just like email us or something. And then basically like molecules will mix with like molecules. So polar molecules mix with polar molecules, and non-polar mix with non-polar. But that's just a bit of extension. Cool.
Yep, and next we've got a quick video to show you using an example called oobleck. And some of you may have heard of oobleck before, but if you haven't, just watch the video and you'll see how it relates to our topics, states, and mixtures.
You know what we haven't talked about in a while? Things things that matter, like mass and materials and particles. I guess what I mean is things that have to do with matter. We've already talked a lot about the different states of matter. You know, some matter comes in the form of a solid, others in a liquid, and still others in a gas. But are you ready for a question that will bend your brain a little? What if there's matter that fits into more than one of these categories? Is there such a thing? If there is, what's it like? And can I make some? Maybe in my kitchen. Before I answer any of these questions, let's take a closer look at different states of matter. You remember what a solid is. It's matter that has a definite size and shape, like this desk that I'm sitting at, or the clothes that I'm wearing, and, well, all of me. I'm a person with a definite size and shape. Liquid is matter that has a definite size, but no definite shape. The water in this glass is a liquid. It has a definite size, but no definite shape. Like, you could say that my desk is desk-shaped, but there's no such thing as water-shaped. And a gas is matter that has no definite size or shape. The air around me and you is a gas. It's not shaped like anything, and its size changes depending on how big the container is that it's in. Now, all solids, liquids, and gases are materials, or objects made of matter. And all materials have properties or traits that help identify them, like their color, or shape, or size, or temperature, or weight. And now that you're properly refreshed on the states of matter, I'm going to cheat and answer our big question a little early, or at least part of it. Yes, some materials aren't so easily lumped into just one state of matter. These unusual materials can actually act like multiple states of matter. Neat, right? Want to meet just such a material? Then let me introduce you to non-Newtonian fluids. The what now? Non-Newtonian fluids are substances that don't behave like we expect them to. These fluids might look like one thing, but they behave like another. So, what makes a substance non-Newtonian? Let's find out by making a non-Newtonian mixture of our own. Say hello to oobleck. Believe it or not, I didn't make this word up. It comes from a book written by Dr. Seuss. You know, the guy who wrote The Cat in the Hat. In another book he wrote called Bartholomew and the Oobleck, there's a king who gets bored with normal, everyday weather, so instead he makes sticky stuff fall from the sky. That's where oobleck, the stuff that we're going to play with today, gets its name. But the stuff we're talking about is real. Our oobleck is a non-Newtonian substance with a pretty simple recipe. No magical kings required. All you need is about 1.5 cups of cornstarch, about 1 cup of water, a big bowl, and a spoon. Pour the cornstarch into your bowl and slowly add some water. Keep stirring until the mixture feels kind of like honey. In the end, it should look like this. Now grab some of this goo in your hand. When you squeeze it, it'll form a solid ball in your palm. But when you unclench your fist and release the pressure, it'll slide between your fingers, like a liquid. All fluids have a property known as viscosity, which is basically the rate at which a fluid flows. And Newtonian fluids, or normal fluids, flow at a consistent rate. But non-Newtonian fluids, or non-normal fluids, flow at a different rate depending on how much force or pressure is applied to them. So your oobleck flows at a much slower rate when pressure is applied to it, acting like a solid. But when the pressure is removed, it flows faster and behaves like a liquid. Good for you, oobleck. Being normal is overrated, right? So if an object's viscosity or flow rate is not constant or changes depending on the pressure applied to it, it's a non-Newtonian fluid, which means, yes, some materials can fit into more than just one state of matter. These materials are called non-Newtonian fluids, and they don't play by your regular rules of matter. They'll be a solid sometimes, and then a liquid at others. You do you, non-Newtonian fluids. I like your style.
Yeah, so that was just a quick fun little video about oobleck, and you guys can of course try that at home if you like. Just try to make too much of a mess and but yeah, certainly a fun little thing to do and think about how the solids and liquids kind of interact with each other and why they form both a solid and a liquid. And this concept about non-Newtonian fluids, we didn't really touch on, but if you want to investigate, if you want to advance yourself, feel free to do some of your own research, or, you know, just email us if you want to know more, or we can set up an activity for you if you guys are interested in that sort of stuff.
All right, with 2 minutes left, let's wrap up really quickly.
Yeah, okay, good.
Quick recap. So we have covered the types of particles. We have atoms, ions, and molecules. The three states of matter: solids, liquids, and gases. And we also have types of matter: elements, compounds, and mixtures. So everything's occurring in threes today for some weird reason. We also talked about physical and chemical changes and classified some of those. And then we had a look at pure versus mixtures, and also the types of bonding involved in molecules. Cool, pretty good, pretty